In this lecture, I'm going to talk about von Neumann programming paradigm and other computing paradigm. In the previous lecture, we talked about this control-based computing model. Now, we are going to talk about it in more detail and also look at other future computing paradigm. First, let me introduce this great gentleman, John von Neumann. He is so important. He's a famous mathematician who invented modern computing model for all the computers we have seen so far in the market. Most of the computers we see today is actually of this von Neumann model. Von Neumann was an important figure in computer science. His major contribution is the use of memory in digital computers to store both sequences of instructions, that's program, and data. And this invention was a breakthrough to which von Neumann made major contributions. You may wonder why it is so important to have memory. And for today, we have terabyte, gigabyte, a lot of memory. And why the people at 1930s, 1940s didn't know about this important invention. So von Neumann also created a field of cellular automata without the aid of computers, constructing the first self-replicating automata with pencil and graph paper. So basically, it created a self-reproducing automata. That's the birth of the artificial intelligence. And in his invention, memory is one of the central themes in his book. And here I'm going to talk about why memory is so important in von Neumann machine. Imperative language. Imperative language is by commands or orders or instructions to the machine. And von Neumann language predominate the whole market, and because it can store the program in the memory. So, imperative language has largely depend on von Neumann computing model. They will occupy the bulk of our attention. We also plan to spend a lot of time on functional and logic languages, but basically the most important discussion for this course will be on imperative language, and that's based on the von Neumann machine model. And we have briefly talked about this model before in previous lecture. Basically, it comes with memory and logic unit and some register, that's accumulator, or you can call it register. So basically, the whole machine have a main memory, I/O unit. Both memory and I/O unit will be loaded to certain register, and this controls unit that fetch the instruction or program in the memory and use that program to perform operations on this ALU unit. We call it arithmetic logic unit, and this ALU unit will load data from the memory or from the I/O and do some processing and store back to the memory, and the whole program is controlled by the control unit. This we call it von Neumann machine model, and modern microprocessors are based on this von Neumann machine model. And it is so simple right now, but in the old days, this invention is very important. So this is the computer architecture for imperative languages. First, let's look at the automata theory. Basically, we have combinational logic, finite state machine, push-down automata, and Turing machine. Combinational logic only has logic, so there is no memory. Finite state machines start to have some memory using data latches. And then push-down automata, including the stacks. And finally, general-purpose Turing machine has tape memory for I/O and also the reading head. And these are different levels of the automata theory. But in theory, everything can be done in Turing machine, can be done in combinational logic as well, but they just have different level of complexity in terms of machine configuration. But functional-wise, they are equivalent. First, let's look at combinational logic. Theoretically, for any output and any input, for any n-bit output with n-bit input, you can basically design any combinational logic to produce any combination of the output that desired by those inputs. So every computation that can be done in any computer, like the Neumann machine, can all be done by combinational logic. A certain logic design is like here, but because it can be very complicated, so some convenient model were invented, including this Neumann machine model. And the application of the combinational logic today still are widely used in ALU, code, or arithmetic logical function like adder, subtractor, comparator, programmable logic devices, and data transmission, multiplexer, demultiplexer, encoder, decoder, and code converter like binary coded decimal or 7-segment display. Second, beyond the combinational logic, we put the memory in there, operate with the combinational logic, it will become a finite state machine. You have input, and with the state variable stored in the memory, or state bits stored in the memory, we can create some output, and this is called Moore machine model, but this is the simple finite state machine. And Neumann machine model actually is more complicated compared to this machine. Again, finite state machine can all do whatever been done in Neumann machine. And in the finite state machine, we have mini machine and Moore machine. The Moore machine produces the output based on the state variable. And the mini machine produces the output based on the input as well. So let's look at the difference between these two machines. For Moore machine, the output are functioned solely on the current state, and output change synchronously with state changes. Mini machine output depends on state and input. So both state variable and input may change the output. And the Moore machine, the output is only depending on the state variable. And for mini machine, the input change causes an immediate output change, so the output is asynchronous. But theoretically, you can put the equivalence of these two machines. Whatever can be done in mini machine can all be done by Moore machine, except that the asynchronous feature for mini machine. And beyond the finite state machine, recently we also have faulty logic machine. For our current binary logic, we only have 1 and 0, but faulty logic have a grade level for different logic level. That's not completely sure, and some machine can be built using this faulty logic machine to control washing machine and a lot of electronics being controlled by faulty logic. And I introduced this because this actually moved beyond current computation model of the Neumann machine paradigm. And we have some other coming up. And also for neural network computing model, it can be used for image reconstruction or pattern recognition. And basically, the neurons are the basic computing model, and these neurons can be analog or digital. And actually, the performance of these neurons doesn't perform in the same way that Neumann machines are doing. And I introduced faulty logic and neural network just for comparison of the newer computing model with the existing logic-based computing model in Neumann machine. And also, there are DNA computing. Using the encoding nature of DNA, you can read in DNA source and do information encoding and hybridization, and doing DNA mutation and decode and send out the output from the decoding data. And you get the output and send the data back to the methodology tool. And this is the DNA computing model. And for computation, we can have the computing model, Neumann machine, rule-based, fuzzy logic, neural network, and DNA. This we call it computing model. And for programming, paradigm, and architecture, we are using Intel Core 7. So this one is implementing the Neumann Machine model. And this is the second level. It's a higher mathematical model. And this is the process level. And for programming language, utilize this programming model is our example language C or C++. And this gives you an overall idea of computing model versus programming paradigm versus programming language. So right here, I introduced fuzzy logic, neural network, and DNA computing paradigms. All of these are different from the Neumann machine. And Neumann machine, we introduced the combinational logic finite state machine. We haven't touched the push-down automata and the general purpose Turing machine and Neumann machine itself. And these two topics, the push-down automata and the Neumann machine language, is one of the topics that we will cover in this course. We are going to introduce it in the first unit. Thank you. Bye.